Welcome to my YouTube channel Cognara. I'm Michael, your science and technology educator. Today, we are going to talk about something that has quietly unsettled modern astronomy. It is not a rumor, not speculation, and not science fiction. It is a real discovery, based on new observations, that is forcing scientists to pause and reconsider what they thought they understood about the universe. This is one of those moments in science when answers create deeper questions. And those questions may change how we understand the cosmos itself. For decades, scientists believed they had a reliable model of how the universe works. They knew how it began, how it expanded, and how it evolved over time. The equations were not perfect, but they worked well enough to explain most observations. Then new data arrived. And suddenly, the universe started behaving in ways that did not fully match the model. The source of this shift is not a single experiment. It is the result of several independent observations, made possible by a new generation of instruments, especially powerful space telescopes and precision measurements of cosmic expansion. To understand why this discovery matters, we need to step back and talk about one of the most important ideas in cosmology: the expansion of the universe. Since the early 20th century, scientists have known that the universe is expanding. Galaxies are moving away from each other, and the farther they are, the faster they appear to recede. This observation led to the idea of the Big Bang and shaped modern cosmology. For a long time, researchers believed they could measure the expansion rate precisely. This value is known as the Hubble constant. It tells us how fast the universe is expanding today. But here is where things become strange. When scientists measure the expansion rate using observations of the early universe, they get one value. When they measure it using nearby galaxies and stars, they get a different value. And the difference is not small. It is large enough that it cannot be easily explained by measurement error. This disagreement is now known as the Hubble tension. At first, scientists assumed the problem would disappear with better data. But as measurements improved, the tension did not go away. It became stronger. This is one of the first cracks in the standard model of cosmology. Then came new observations from powerful space telescopes that allowed scientists to look deeper into the early universe than ever before. What they saw was unexpected. Some galaxies appeared larger, more structured, and more evolved than they should have been so early after the Big Bang. According to existing models, these galaxies should not have had enough time to form in such complex ways. Yet there they were. This raised an uncomfortable question. Either our understanding of galaxy formation is incomplete, or something more fundamental about the universe is missing from our theories. And this is where the idea of dark energy enters the story. Dark energy is the mysterious force believed to be driving the accelerated expansion of the universe. It makes up most of the energy content of the cosmos, yet we do not know what it actually is. For years, dark energy was assumed to be constant and stable. A quiet background force that behaves the same everywhere and at all times. Recent data suggests this assumption may be wrong. Some observations hint that dark energy might not be constant at all. It may change over time. If this is true, it would mean that one of the foundational pillars of modern cosmology needs revision. And when a foundation shifts, everything built on top of it must be re-examined. This does not mean scientists were careless or mistaken. Science works by building models that best fit available evidence. When new evidence appears, models evolve. This is not a failure of science. It is its strength. But the scale of this challenge is unusual. The standard model of cosmology has been remarkably successful for decades. It explains the cosmic microwave background, large-scale structure, and the distribution of galaxies across billions of light-years. Now, small but persistent inconsistencies are appearing across multiple areas. Each one alone might be dismissed. Together, they form a pattern. Another piece of this puzzle comes from measurements of gravity itself. On very large scales, gravity does not always behave exactly as predicted. Some scientists are exploring whether gravity works differently across cosmic distances. If gravity changes subtly over vast scales, it could explain some of the strange observations. But this idea requires modifying theories that have worked extremely well in other contexts. Again, this creates tension. What makes this moment especially important is that these discoveries are not isolated. They come from independent teams, using different methods, observing different parts of the universe. This convergence suggests that the universe is not simply hiding small details. It may be pointing toward something deeper. Some physicists believe we may be approaching a shift similar to the one that occurred a century ago, when classical physics gave way to relativity and quantum mechanics. At that time, familiar concepts like absolute time and space had to be redefined. Today, the questions are different, but the feeling is similar. What if our understanding of dark energy is incomplete? What if the early universe behaved differently than we assume? What if the laws of physics themselves evolved over time? These ideas sound radical, but so did many ideas that are now considered basic science. It is important to remain careful here. No single discovery has overturned modern cosmology. The existing model still explains a great deal. The cracks are real, and they are being taken seriously. This is a moment of uncertainty, not collapse. And uncertainty is often where the most important progress begins. What we are witnessing is science in motion. Not the finished answers, but the process of questioning, testing, and revising. The universe has always been more complex than our descriptions of it. Each time we think we have reached a final understanding, new observations remind us how much remains unknown. This discovery does not tell us that everything we know is wrong. It tells us that our knowledge is incomplete. And that is not something to fear. It is an invitation. An invitation to explore deeper questions about the origin of the universe, the nature of space and time, and the forces that shape reality on the largest scales. For viewers like you, this is a rare opportunity. You are witnessing a moment when science is actively rewriting parts of its own story. Years from now, we may look back on this period as the beginning of a new chapter in our understanding of the cosmos. Or we may discover that the answers are subtler than we expect. Either way, the universe has reminded us of something important. It is not obligated to fit neatly into our theories. And that is what makes it endlessly fascinating. Thank you for spending this time with me today. If you enjoy calm, thoughtful explorations of science and the universe, you are exactly where you belong here at Cognosra.